What's up, you guys? Welcome to Integration Bee Training for Advanced. This is part 12.6, and in this section we're going to be constructively summing. What on earth does that even mean? What this means is that we are now going to combine the use of manually integrating and the summation as well. Okay, let's go ahead and start with our first integral example. Can we forcefully u-sub this? Yes, we can. Right? Yes, we can. If you have the chance to, do it. Do it. Okay. So, let u equal the square root of x first. You know, deal small things at a time. 2u, 1 over u, and then 1 over u. This is now 1 to infinity. This is going to give me 2 over u cubed of u du. Okay? And now that we can simply integrate this, this is actually not so bad. N equals to 1. We have n. And then from n to n plus 1, we have 2u cubed du. This is going to equal to negative 1 over u squared. So what we have is n equal to 1 of n of 1 over n squared minus 1 over n plus 1 squared. Yeah. And so now what we have, we could just simply simplify this. This is going to be what, n plus 1 n plus 1 squared minus n squared is equal to 2n plus 1. And then we have n squared. Well, we cancel that out. So with n plus 1 squared. Now I think about it, I think it's better to leave it separate. I think it was better to leave it separate. Now I think about it, so just distribute the n. We have 1 over n, and minus n plus 1 square. But we could just do plus 1 minus 1, right? So now this would have been 1 over n minus n plus 1. And then plus n plus 1 square. Okay? And so now our integral, our answer was just simply, what, 1 pi squared over 6 minus 1. Yeah, so this just cancels out to pi squared over 6. Okay? Cool. So that's just straightforwardly summation, right? But now you're probably asking, okay, but why is this video about constructively summing? What does constructively summing mean? And what do you mean by using manual and sums at the same time? Let me show you what I mean by that. Okay? Remember this. Remember this sum. Okay? And you'll see why. So let me just Control Z everything. I forgot it has a limit, so let me just erase this then. Okay, so starting here, what does constructively summing look like? To constructively sum this, so first of all, you can't plug in 0, right? Because, I mean, it's at the bottom. So what we do is we start at the top first. Okay, so let's see, 1. From 1 to, well, let's see, how do we go about this? So what makes this 1? At what interval is this whole floor function going to equal to 1? If we plugged in 1/4, right? This would be, this would equal to 2. And we would have 2 as our ceiling point. Aha! So our bound from 1/4 to 1, between 1/4 and 1, this is going to equal to 1. From 1/4 to, okay, what else? What's going to be from 1/9? 1/9 is going to equal to 3. So 1/9 here. So I'm going backwards, right? I'm starting from 1 and working my way to 0, right? But notice that we're never going to reach that 0. We're never going to reach that on time because it goes on infinite. It's infinitely, right? That's why we use summations, so that we solve for the series, and that helps solve the integral, okay? Because graphically, you're just summing up rectangles. That's all you're doing, okay? And that's what constructively summing looks like. This, you are constructively summing, right? Okay, oops. Okay, so we have 1. Okay, so we have 1 from 1 minus 1/4. Okay, plus 2 times 1/4 minus 1/9. Okay, plus 3 times 1/9 minus 1/16. Okay, and it goes on forever. And then, wait a minute, there's a pattern. If there's a pattern, that means we can turn this into a sum. From n equals to 1, okay, n, we have n, what? This is 1 over n square minus n plus 1 square. Wait a minute. What is this? This is the same sum that we just solved. This is the exact same sum that we solved, right? This is what constructively summing looks like. And there are some integrals where you can't do a force U substitution. So because of that, we have to stick to constructively summing. And this is what constructively summing looks like. Okay? Alright. And this also leads to pi squared over 6. Alright. To the next example. Let me show you what happens if you just try to force U substitution. Okay? Alright, so let's say, oh, okay, let's just, there's this inside. Log 2024 of x. Okay. Then, let's see, 2024u is equal to x, right? And then you derive this and you're like, oh, okay, this is 2024u ln of 2024 du equal dx. Alright, perfect. So then you go ahead and plug in, okay, this is u times 2024 u ln of 2024. Alright, easy integral, no problem. Blah, blah, blah. Right? And then, okay, but I gotta plug in the balance. Alright, so 1 is 0. Okay, plugging 0 in, that's gonna be give me negative infinity. Okay. Wait. From negative infinity to 0, what do I do? Do I just go like this? I don't think so, right? And now you're probably thinking, okay, wait. Okay. We could just switch, let w equal negative u, whatever, right? Just switch, you turn this into positive infinity. Just switch it, right? Just switch it. Okay, but then you have like a negative u as your floor function. Now what? Right? Now what do you do? Would you just call it negative n, or? I mean, I don't know if that works. Now I think about it, I don't know. I don't know if that works. But okay, okay. So this is awkward. You don't want to risk it. I don't want to risk it. This does not work. Okay. Well, and then you're probably thinking, wait, but I mean, if that's the case, then you just King's rule, right? Let's turn this into log of 2024 1 minus x instead. Now we can go ahead and u substitute this. All right, let's force it. Force u substitution, and then you're like, okay, this is 2024 u equal 1 minus x. X is equal to 1 minus 2024 u, and then you do the dx. Okay, this is what, negative 2024 u ln of 2024 du. Okay, and so now I go ahead and plug in my bounds, plug in 1, I get negative infinity, but I mean with this negative, I'm sorry, wait. Plug in 1, I get 0. Wait. Huh. This still does not work. This seriously still doesn't work. Huh. Alright, if I plug in 0, and if I plug in 1, I get negative infinity. Interesting, right? Oh, okay, and it flips, and then it flips. Yeah, negative infinity to 0. Yeah, same thing. Yeah, King's Rule does not help either. So, you see the problem? You see why we have to constructively sum? So, there are some times where you can't just do a U substitution. You just can't. You just can't. So, instead of summing it equationally, we have to manually sum it. Manually sum it. Constructively sum it. Okay. So how do we start that? Okay, well, first off, we can't start with 0 because that's undefined. So we start at the top instead. Alright, so 1, okay. And what makes this equal to 1? Well, what makes this equals to 1 is we need 2024. Okay. But we don't have 2024 on top. So I guess we're going to go in a negative direction where we let x equal 2021 over 2024. Then that's going to give us negative 1. Okay, so I guess we're going to go negative here. Okay. Alright. And then to make this, and if I want this to be negative 2, I need, let's see, we know this is going to be 1 over 2024. If I want this to be negative 2, I need 1 over 2024 square. And then if I want this to be negative 3, I want this to be 1 over 2024 cube. And then it keeps on going because we can never reach 0. Alright. Constructive summing. Okay? Very useful. You see why? You see why we can't do the sum is because it was actually going towards negative infinity. It really was. Okay? We just couldn't, you know, sum it. And we didn't know how to deal with this. Or at least I didn't. But I don't want to risk it. I think it is safe to, I mean, I don't know if this is true. It could be. But I could be wrong. I don't think so. But I could be wrong. I feel like there is a formula for that. But constructive summing works. So here, to practice for safety reasons, we're going to go ahead and just constructively sum. We have 1 minus 1 over 2024, and then minus 2 of 1 over 2024 minus 2024 square, minus 3 of 2024 square minus, and then the cube version of that, then it goes on forever, right? So what we have is we have a negative sum where we start with n equals to 1, and then we have, is it n equals to 1? Because we have 2024 n here, right? But then when we go on the second term, we're going to have n, well, I don't know why I didn't put n at the front. I should probably just do that. N at the front for 1. And then here, This is n minus 1. N minus 1. Okay, interesting. So, this is our sum. So we technically have n equals to 1, and 1 over, I'm just going to flip it. N minus 1. I just noticed something. Yeah, we could just factor out the n in 2024. And what we have is 1 minus, and this is 2024 negative 1. So we have 2024. 1 minus 2024. Okay. So we have negative 2023 of the sum n equals to 1 of n 2024 to the power of n. How do we solve the sum? I'm just going to let a equal 2024 and call this sum s n a over n. Right. So for s, we start with n equals to 1, and we go up to infinity. So we have 1 over a, 1, 2a squared, 3a cubed, and etc. Right. A times s is 1 plus, and then we have 2 over a, 3a squared, and then etc. Whatever. Okay. And then if I let a minus 1, or sa minus s, we get s times a minus 1. This will give us 2 over a minus 1 over a, it's 1 over a. 3a squared minus 2a squared, 1a squared. Again, the whole intention is to turn this into a geometric series, which would give us 1 over 1 minus 1 over a. We can simplify that to a minus 1, and then divide this a minus 1 to the other side. So s is equal to a over a minus 1 squared. Aha! Again, obviously I won't be able to memorize this, but I at least know how the process goes. So, plugging in a 2024, this is going to be 2024, 2023 squared, right, times negative 2023. So our answer is going to be negative 2024 over 2023. Okay, so the answer to that whole integral is literally negative 2024 over 2023. That is our answer. Okay? So again, sometimes u-subbing probably doesn't help, or it gives you an off vibe. So if you ever come across that, constructively sum it, and then create your own summation form, and then solve the sum. Okay? Now let's go ahead and apply that in this one. Okay? So, again, we cannot do a forced u substitution because it'll give us negative infinity to 0, and we can't turn that into a sum. Otherwise, we'll have ambiguity, and we don't want to risk our answers. Okay? So, let's go ahead and quickly construct a sum. So, of course, we have to start with the top because 0 is undefined. So, starting from 1, I want this to be 1, right? I want this to be a 1 or an integer. But we don't have 2024 in our bounds, so we have to go smaller. Okay. 1 over 2024, that's going to give you negative 1. Okay. We got that. 1 over 2024 is going to give us an integer. Okay. 1 over 2024. How about negative 2? Okay, we need 1 over 2024 square, right? 1 over 2024 square, and if we want negative 3, we're going to need 1 over 2024 cubed. Right, and this continues, again, infinitely. all the way to, well, you'll never reach 0. So what we have is we have negative 1, okay, 1 minus 1 over 2024 minus a half 1 over 2024 square, and minus 1/3, etc. Okay, so it's like the exact same thing. We construct a sum, right? Infinite. Here we have what? This is n equals to 1, right? We have n. Well, we have 1 over n this time. So we have 1 over n this time, and it's the kind of similar, a similar case, right? Okay, so what we have is from n equals to 1 to infinity, we have 1 over n. So this time it's 1 over n, and then the rest seems to be the same thing. 2024 n, we can factor that out, and we're left off with like 1 minus 2023. Yeah, negative 2023. Okay. Cool. I like how I didn't put that in yellow, but I'll put that in yellow in the next part. I mean, in the next step. Okay. So, cool. So what we have, our sum is negative 2023 from n equals to 1 of n 2024 n here. All right. Do you remember? Now this, oops, let me put this in blue. Now this is Taylor series. This is Taylor series. Xn over n is equal to ln, negative ln 1 minus x. Remember that there's a negative. So here, we technically do have a negative. So, and then x is just 1 over 2024. So our answer here is the 2023, don't forget that, 2023, of the ln of 1 minus 1 over 2024. So our answer is 2023 times the ln of 2023 over 2024. Okay? And there you go. Right? You don't have to pause and hesitate, worry about something. Just manually sum it. Okay? Constructively sum this integral. Alright, let's do another example. Let's go ahead and solve this integral here. Again, if we try to do a forced U substitution, we might end up having to do, we'll end up with a negative infinity, and we'll have ambiguous problems. So let's go ahead and manually construct a sum with this. So we'll start with 2, because again, 0, we can't plug in 0. So for 2, we have 1, right? If I plug in 1, I get 0. Oh, wow, we should look at that. So we have 3/4 between 1 and 2. This is going to be 0. Okay. And then plus from 1. Alright, what's next? So, well, we can't plug in 0. But we can have negative 1. And to have negative 1, we get a half. Okay? So this would give us a negative 1. And with 1/2, we can get 1/4. Because that would give us negative 2. Right? It's going based on log 2. So we get 1/4, 1/8. 1/8 would give us negative 3. And we keep on going. Okay? Cool. So this is we already see a sum here, so that's perfect, right? Oh well, we gotta write it out first. So we have 3/4. I'm gonna write it like this, just for ease sakes. 2 minus 1 plus 3/4, 1 here, and we have 1 minus 1/2 plus 3/4. Oh, I'm sorry, this is -1, -2, and then we have 1/2 minus 1/4, and then so on. Okay, so our sum starts with 0, and I believe that we actually have what, 4/3? Yeah, 4/3 n, and then we have 2 minus 1. Well, this is just 1. 1/2. Wait, this is equal to 1/2. This is equal to 1/4. 1/4 minus 1/8 is 1/8. Wait a minute. This is also going by a half as well. Would you look at that? So what we have is a simple geometric series. This is just 4/6, 2/3 of n. Perfect. So now our answer is 1/1 minus 2/3. This is equal to 3. Alright, so this integral satisfyingly equals to 3. Okay, well there you go. Another great constructing a summation example. Okay, so we have sine pi over x. Okay, a lot of composite stuff. If we try a u substitution, right? So let's let u equal pi over x. This would give us what? This would give us pi 0 to infinity. Okay, so this would give me pi to infinity, and then we would end up with pi sine of u squared. Now, are you sure you want to do w equal sine of u? Do you want to do that force u substitution with sine of u, or do you want to leave it? Right. So another reason why we do constructive summing is we could get something like this as well. And here, you know, if we do w equals sine of u, then we have square root 1 minus w squared. It's nasty. Okay, nasty. I don't know if you want to deal with that. So, how are we? Oh, and we also have like inverse sine of u. Yeah, with infinity, I don't know. Yeah, that's also more ambiguous stuff. Okay, so with that in mind, how do we solve this? Again, we have to constructively sum it. Now, this is actually very difficult to do. This is actually a very difficult case, and let me explain why. Here we don't know. So sine of u, it can only equal either. Well, within integration, it can only equal to 0 or -1. Right. So if we draw a unit circle, okay, sine of u goes from y-axis. So anything here is going to equal to 0, right? Anything here is going to equal, I don't know why I'm coloring that region. It should be this. Anything here the value is going to equal to -1. So what we're going to do, oops, this is still green. So we're going to have to split it. So from pi, from what? Let's see. We're going to have, so we're starting with pi, and we're going upwards to infinity. So from pi to what? Pi, that's going to be 0. From pi to 2 pi, right, this is going to be -1. So we have -1 throughout, right? Pi to -1 throughout. We ignore the, I'm sorry, when we go upwards, we ignore 1, because when you integrate, it's just going to be like a point, but then the rest is like this, you know? And then you have like rectangles, but there's like nothing here. So it'll literally just be like this. Like there's nothing when you integrate the area under the curve of the function. Okay? Just a point. That's what that is. So we ignore 1. Okay. So with that out of the way, pi, so -1 from pi to 2 pi. From pi to 2 pi, it's always going to be -1. Okay. U square du plus, okay, now what? From 2 pi to 3 pi, from 2 pi to 3 pi, well, it's going to equal to 0, because it's less than 1. So this whole thing is 0. Okay, great. And then from 3 pi to 4 pi, it's, you know, the same thing, -1. So it's going to be alternating -1, 0, -1, 0, etc. So all we're going to get is 3 pi, 4 pi, 5 pi, 6 pi of -pi over u square, 7 pi, 8 pi of -pi over u square. Okay, so we have -pi, I'm sorry, we'll keep the negative so that when we integrate, it's just 1 over u. So we have pi, and then 1 over u, we get 1 over 2 pi minus 1 over pi, right, when we plug 1 over u. So, yeah, when we integrate, we get 1 over u, and then plug in 2 pi minus 1 over pi. Okay. What else? Plus pi of 1 over 4 pi minus 1 over 3 pi, etc. And it keeps on going. Okay. Another thing I like about this is that all the pi's cancels out. So what we technically have is a half minus 1 plus 1/4 minus 1/3. Wait a minute. Does this look familiar to you? Oops, I'm sorry. That should be 1/6 minus 1/5. Yeah, this looks familiar. What does this look like? This looks familiar. This looks familiar. What we technically have is -1 plus a half minus 1/3 plus 1/4. I'm just rearranging it. I'm just rearranging it. Right, oh, minus whatever, dot dot dot. What is this? This is literally this. It's Taylor series. This is equal to -ln of 2. And that is our answer to that integral. That sign-looking integral surprisingly equals to the -ln of 2. Okay? Alright. Again, very useful. Right? You might think you could just u sub everything, but no, not always. Especially complicated ones, it's better to just constructively sum it. Manually integrate it a little bit, but it's kind of like doing manual and sum at the same time. Manual first, and then turning it into a sum. Okay? Alright. To give you, I'm not going to do this, but I'm just going to throw this one at you. You can do this on your own. Go ahead and try doing the cosine version of it. Alright. You should not get a logarithm answer. I'll tell you that. You should not get a logarithm answer. Okay? So, try that one on your own. It does involve Taylor series, but it's a different Taylor series. So I'll give you that as a hint. But that's how you know you're on the right path if you have a different Taylor series. Yeah, I'll let this integral surprise you. All right. So yeah, definitely. I think that's about it. Yeah, this is the last part for the whole integration, piecewise integration series. So in the next video we should be starting part 13. Okay. So yeah, practice these integrals on your own so that you get more comfortable, especially constructive summing. Constructive summing is not a comfortable method, so definitely get comfortable with this. Okay. All right. Thank you guys so much for watching, and I'll see you guys in the next part. See ya.